Here's a curve. I don't think I'm exaggerating. I know I'm definitely not exaggerating when I say that this is the single most important thing in this entire course. And tangent lines are the basis of something called a derivative. A derivative is the basis of calculus. Right? You don't have calculus without a concept called the derivative, and you don't have derivatives without tangent lines. Right? So this, hopefully, because when I first started teaching calculus, I sort of took this connection for granted, and so I decided, it'd probably be a pretty good idea to actually investigate the relationships, because people could regurgitate what a derivative was. Slope of the line tangent to a curve at any point along a curve. That's fast and not overly meaningful right now, but by the time the course is over, I'll say, what's a derivative? And you'll spit that out and you'll be like, whoa, where did that come from? It's a question of whether or not you understand what it actually means, right? And hopefully this activity is going to get us there. All right, so a tangent line to a curve or function. Well, I'll draw it, or I'll draw a tangent line. Here's a point, and there's a tangent line. A line that touches a curve at only one point. A line that touches a curve at only one point. In geometry, we did a lot with tangents when dealing with circles. And we knew that, okay, so here's something, whether it's stuck or not is a different story. What's the relationship between the tangent of a circle and a radius of that circle? Tangent to a circle and the radius. How do they, they're perpendicular. They relate to each other because they're perpendicular to one another. Right? So, and that fact is going to come into play tomorrow. So it's pretty important. So the cool thing about calculus is those previous years of all disconnected math will finally start to become connected. You're like, oh, that's why I was learning that. They'll start to make sense. All right. A secant line to a curve or a function. Because we know what a secant is for a circle. What is a secant to a circle? Exactly.
It's like a line that just passes through the circle and like 2 points, or not the line. Yeah, it could be.
No, that's exactly it. Line of passing through a circle, intersecting at 2 points. That's what a secant is. All right, but we want to do it to a curve or a function. Ooh, copter away.
We watch it?
No. I mean, not here. You can watch it on your own time. Hold on, I'm going to make that a little curvier. And put a little bit more enthusiasm into it. So for a function, it's the same general idea. But obviously for a curve, not, any curve, not just a circle. All right, so a line intersecting a curve at 2 points. All right, now we define a secant as just being the line segment connecting those 2 points. So that's the shift. So the secant line would be a line that intersects a curve at 2 points. But the secant itself, when we say something is a secant, it is the line segment connecting those 2 points. All right, so a secant line is just the extension of the secant.
Isn't that like a chord in a circle?
A chord Yes. So a chord is a special type of secant. It's a limitation of a secant. And the largest chord within a circle is known as the diameter. Okay, so yeah, we remember some geometry. That's good. Gotta give credit to the old geometry teachers there. It's like something stuck. All right, so that's the terminology, sort of like the opening monologue, I guess. If you're in Mr. Cohen's class, you know what that meant. Anyway, so you're going to graph a given function, f of x equals x squared, so on the graph grid. Draw a secant 1. Secant number 1 connects these 2 points. All right, and then you're going to create additional secants. You just follow the instructions, and when you do that, all right. When you follow the instructions, you're going to have a bunch of different secants. You'll be able to figure out not only coordinates, but also distances and slopes. Once you complete this table, you will make a startling realization. All right? And that startling realization is the foundation of calculus. All right? And it's one of those things, it's like, I mean, you need to do some thinking along the way. So that startling realization only happens if you do the thinking of why am I doing this? Why am I doing that? Why is he doing that? All of these things would have to come into play, because if you're just waiting for, you know, at the end of the line, you're like, okay, I'm not startled by this realization. This activity sucks. It still might suck, but it has nothing to do with that. That's not why you didn't have the startling realization. It's just because you were going through the steps. You're just like, okay, now I draw a line, I do this. You're not thinking about why you're doing what you're doing. Right? So work together, talk it over. You don't need to finish it today, obviously. Tomorrow you'll have time to work on it. But take your time and really think about why you're doing what you're doing. And I promise there's a serious payoff at the end. That aha moment that made me want to be a calculus teacher. So.
What?
No, that chair's fine. It's the one in the corner that had the protein spill.
I don't like
Protein spill.
No,
protein for lunch.
you're thinking along the right lines. It's not that.
I don't know.
Yeah, we're getting into, like, you won't be eating for the rest of the day territory. So f of a ended up being what? 9. Oh, is this on? No, it's on. It's on. Okay, now it's on. Yeah. Okay, so the b values. So I want to go, well, basically following our progression in the chart. What was my first b value? -2. And my second one?
4. Oh, no. Wait.
No, my second b value.
Sorry, yeah. Oh, 1. Wait.
Oh, so was it -2?
Positive 2.
+2. Then 1. Decreasing by 1 every step of the way, right?
Yep.
So my bad. I'm so sorry.
Hey, it happens to the best of us. What do we get for the f of b's?
4, 1, 0, 1, 4, 9.
And it sure is. All right, so then we get to the part where the startling realization should start to happen. Right now it's very procedural. It's just plotting points, right? Creating a table. It's like not overly meaningful. The h, because as I was walking around yesterday, I saw a lot of people. I mean, and this is a good thing. It's good that you knew this. Breaking out the distance formula and getting answers with radicals in it. That was exciting. It meant that you knew something. It just wasn't the right something. In this case, it's much simpler than that. All I'm looking for is the horizontal distance between 2 points. All right, so I want the distance between the a value and the b value. 5.
8, 9.
78, 42. That's all right. -3 to 1. 4.
This first one.
3, 2, 1, 0. So as we progress, what's happening to my h values? Decreasing specifically towards what?
0.
Okay,
Oh,
so,
it's good at the horizontal distance, or the vertical distance.
well, we don't need that. Yeah. So that horizontal distance appears to be approaching zero. Vocabulary term, it's something that we also use in real life, but we've also been using that extensively in the last unit. That last unit was called what again?
Limits.
Limits and continuity, but limits is really what I'm after here. All right, so the h value seems to be approaching zero. So keep that in mind. Now, my slope, change in y over change in x. So my change in y for the first secant, 4 minus 9 is negative 5, right? But then I divide it by the change in x, which is 5. So that h, we can think of that as the change in x. They're the same thing. All right, so when we're doing slopes here, all we have to do is figure out what the change of y is. So f of b minus f of a. So 4 minus 9, 1 minus 9, 0 minus 9, and so on. All right? And when I figure out all those values, I get my slopes, and those slopes are what?
1.
Positive 1? Negative 1? Followed by?
Negative 2.
Yeah.
Negative 3. Negative 4. Negative 5. 0 over 0.
Right, so that's the question. That's the big question. Do we go back to the formula approach for finding slope? So, I mean, if you're going to change y or change in x in each one, I suppose you would say 0 over 0, but that would be the same as finding the slope between two identical points. If you follow the trend here, what does it seem like you're actually approaching? Negative 6. We have an integer relationship there. All right, so the follow-up question, and this is where the startling realization will happen. It says, if the pattern continued, what would secant 6 become? Well, we know numerically what it would become, but what physically would it be? The secant line becomes a... Oh, what? Well, they're all lines are straight. Okay, well, now we're using terms, so that's good.
I meant but I also don't. Yeah, but I have 6 down. A to B.
So I have 2 points separated, right?
Yeah.
That's a secant. If I move this second point, if I move it closer to the first one, still a secant, right?
Yeah.
But if I get to a point where it's at the exact same location, there would be a line going through that location. What would that line be called? A tangent line, right? Because if those 2 points occupy the same location, that secant line transforms itself into a tangent line. Exactamundo. Slope of the tangent line at x equals, what was it, negative 3? Would be equal to, all right, m equals negative 6. So previously we were not able to find a tangent line slope because the math wouldn't work itself out algebraically. You can't take change of y over change in x with 2 identical coordinates. But if you could figure out where the slopes are going as the horizontal distance between points decrease, then you can get a sense of what you're really targeting, what your slope is actually approaching. What it's actually approaching would end up being the slope of the line tangent to that curve, whatever curve you're dealing with at that particular location. All right? And that, fun fact, is known as a derivative. This entire course is based on knowledge of derivatives. Right? So the slope of a tangent line, and we'll reinforce this throughout the remainder of the packet and the next packet and the packet after that. But the slope of the tangent line is another way of saying derivative of a function. Right? And it's also talking about rate of change, but at a particular moment, not over an interval. When you're talking about secants, you're talking about change over an interval. So you're driving a car, you're commuting to work, to school, whatever. You take the total distance that you traveled, divided by the amount of time it took to get there. That gives you some sort of rate of change, right? It gives you a speed. But is that the speed that you're traveling at every given moment along the trip? No. Right? At some point you were traveling at that speed, but not at every single moment. That's an average velocity, an average rate of change. What we just figured out is the speedometer reading at a particular moment. Right? So when you look at your speedometer and it measures the actual speed that you're traveling at that particular instance, that's a derivative. Right? So that's what we just figured out mathematically. What we need to do is generalize this so that we can work with entire functions rather than specific points, because I would imagine you don't want to create a table like this every single time you have to evaluate a function. All right, but we'll create tables. So we're going to actually continue working with tables until we flesh out properties, relationships, rules that we can kind of, take for granted, I guess, and then go from there. So let me get you kind of geared towards the rest of this, because people were, I noticed anyway, struggling with number 9 because you see A, F of A, B, F of B, and the common question that I was hearing was, well, we had a whole lot of A and F of A on the other page. Which one do you want me to use? The -3, 9, and the -2, whatever? No. I want you to use A, F of A, B, F of B. So if we're writing a formula for the slope of this, I want change in y over change in x in general, but specifically I want the change of that y and that x, or those y's and those x's. All right, so I had the difference between my y values, f of b minus the f of a. Then I have the difference between the corresponding x values, b and a. This is the definition of the slope of a secant, also known as the average rate of change. All right. I wrote a program for our calculators that'll actually do computations for average rate of change. I'll share that with you at some point, but at some relevant point. And this way, if you have a function and you need to know the average rate of change, you can just use the average rate of change program. So it'd be pretty nice for you, I think. The next part of the process is asking us to, well, take it another step. Because what we're going to do here is kind of morph this into something that's familiar, something from pre-calc. So instead of a comma f of a, rewrite the coordinates of a if a equals x. All right, well that's not hard. It's a little weird to look at, but all that's saying is just replace your a's. Is that visible? Not really. I mean, nothing's visible for me. I'm legally blind in my left eye. It's not smart for me to be on this side of the room. I can't see. I can't see. Sure. Oh, wait. This one is weird. Right, I'm going crazy. Kevin, where is he? Was there. Yeah. Okay, I'm not going crazy.
We're having a Home Alone moment. Kevin's not here.
Kevin! Good movie reference. That's like positivity in my mind. When he comes back, he needs to go to golf.
It was a bad day.
All right, so all this is telling me to do is replace the coordinate a comma f of a, replace the a's with x's. That part shouldn't be bad. I mean, because it's just literally telling you to rewrite it with x's instead of a's. The second part is a little bit of a different story because it's saying to write it in terms of x and h. So what we have to do is think about the relationship between the a value and the b value. So going back to the previous page, you can go back, I'm not going to, but because I can just illustrate it here. How did we get from the a value to the b value? In each row, you had an a value and a b value.
You add the distance between them.
Add the distance between them, which is h. So we're taking whatever our x value is and adding h to it, and that gives us our b value. And I know it's like super tiny now, but sometimes that's nice. Okay, so my b coordinate, instead of thinking of it as some new variable or new constant in this case, b, I can relate it to the first coordinate just by noting what the horizontal change is, right? So in my first coordinate, x comma f of x, and this is the truth for any function related stuff, and this is something that's very quickly glossed over in, well, actually that's not a fair statement. It was probably addressed very thoroughly in Algebra 1, but since you didn't see the importance of it, it wasn't necessarily internalized. It isn't until now that you realize, oh wow, that function stuff really was important, right? But what's happening here is whatever your x value is, the y value is a function of that x value. So x and then the f of that x. So if I had a 2 here, the y value would be f of 2. In this case, I have an x plus h, so what's my y value? So x was f of that x. So x plus h, f of that x plus h. It's a function evaluated for the x plus h. So the formula in question number 9, I mean, you could really just kind of plug and chug now, because the f of b is now the f of x plus h. The f of a is now the f of x, but I wouldn't even think of it that way. I mean, you're welcome to do it, the instructions tell you to do it that way, but I would think of it more like, I just need to find the slope of my 2 new coordinates, change a y over change an x. These are my y's. And these are my x's. That's kind of what I was hoping for. The bottom simplifies down. The top you can't do anything with. But that's something that you worked with a lot. Freak out in theory. Regardless of who you had, because that's definitely in the curriculum and it's definitely something you're supposed to take a lot of time with, but in Unit 1, which means like September of last year. So maybe you don't know what you're supposed to do with that, because it's been a long time, but looking at that, you should be like, yeah, that was a thing once. I remember needing to do something with that. I don't remember what to do, but I remember having to do something with it. All right. So that's something that kind of, you know, it'd be nice if it was there, but if not, we're reviewing it. So, and I will say, in all honesty, even if you did learn it, you probably didn't learn the origin story of it like this. Right? It was like, here's a formula, now let's plug some stuff in and get an answer. What does the answer mean? I don't know. Does it matter? It's pre-calc. You'll learn about that in calc. You'll be like, oh wow, that's great. I can wait a year for that. All right, well that sounds like fun. But you know, now we're at the point where I would love it if you knew all that stuff, but I can't take that for granted. But that, you know, let me go with this. Does anybody actually, I mean, I was shocked, one person in the other class knew it. Does anybody know what the name of this ratio is? I'm gonna take a sip of coffee while you think that. But it took like a good 45 minutes of staring contest from the other class. And that was strange because the class is only 40 minutes. So 5 minutes after the bell rang, we're still looking at each other. Yeah, sure.
Oh, just the slope one.
Oh my god, wait.
Well, no, but it's like
right here.
then
I'm not gonna get it though.
What is this symbol?
Minus.
A minus. What's another name for minus?
Negative.
You go.
subtract.
Give me one more.
Inverse.
A high difference.
Indifferent.
Difference.
What is this?
Difference of fraction.
Fraction.
Division.
Division. Result of division is known
Is this synthetic
as quotient.
division?
Oh, quotient.
Difference. Quotient.
Difference. Oh, I do remember that. Yeah.
Yeah, but you know what? So, fun fact. That's the stupidest name in the world. It doesn't tell us anything about what it's used for.
Yeah.
It's a quotient with a difference in it. Thanks a lot. That's so friggin' useful. Like, what does that tell us? What does that tell us about the nature of this expression? Absolutely nothing. But if I tell you that that is the slope of the line segment connecting any 2 points along any curve, that has more meaning. All right? Obviously, it's a little bit more to remember, but that's the foundation of the concept of a derivative. So, knowing what it does for us is way more important than knowing that it is a quotient involving a difference. All right? Number 13, when 2 points used for the secant line get closer to one another, the horizontal distance between them is approaching a value of 0. And that word, whether it's in written form or spoken, keeps popping up over and over again. Right, so that's making it into a tangent. All right, so in the next question, when we want to write the formula for finding the slope of the tangent in terms of x and h, well, we know that we're working off of our secant. We want the points of our secant line to get closer and closer together. So I have to make a minor adjustment to this expression to make that happen. What's that minor adjustment?
Multiply. No. Taking off the 8. How do we do that?
Say
Can we multiply the top and bottom by like f of x plus h
limit
plus f of x?
limit as x approaches 0 or h approaches 0 of f of all that.
Limit as h approaches 0 of f of all that.
But I'm saying like h is on the bottom by itself, so don't we have to do something to the actual limit in order for it to?
Oh, I see what you're
Plug
saying.
in.
Yeah, no, that's a good point. We wouldn't do that until we have a particular function to work with, though, because this cannot be simplified any further in its current form. It isn't until we actually start working with a real f of x. So it's something given, like in the previous problem where it was x squared, or in the next one where it's sine of x. It isn't until we have something particular that we can work on trying to algebraically simplify this. But at this point, all we need to know is that if I have an expression here, a meaningful expression representing the secant, then all I have to do in order to find the slope of the tangent is find the limit as that h value approaches 0.
Oh, you're saying we need an x value?
Yeah, we're going to need like f of x equals x squared sine x, something.
Gotcha.
All right. So then the last example there is asking us to look at the sine function at x equals 0. So I don't mean to teach you all the stuff that period 7 asked questions about, but it seems like as I was walking around yesterday, yeah, it must have been yesterday, and as I was reading those Unit 1 reflections, it seemed like trig was a sticky point. So I didn't think it would be too much of a problem if I took some time and went over it. Right? So the sine wave, we know, exists on the interval of 0 to 2 pi if we're looking for one full wave. It has a minimum value of -1, a maximum value of +1. We talked about this with the sandwich theorem. All right, what we're doing here, because you're kind of left to your own devices a little bit, is we're looking for the slope of the tangent line at x equals 0. So we have our a. A is going to be 0 no matter what. F of anything is asking what is the y value at that particular anything. Right? So what is y when x is equal to 0? 0. Sine of 0 is equal to 0. But even if that wasn't working for you, it's like right here. Right? Coordinate 0, comma, sine of 0. Right? Because again, it's a comma f of a. Notation is going to become more and more important throughout the course. It's like in earlier years, you can kind of fake your way past the notation. Here, it'll bog you down if you don't respect the notation. All right. So I wrote Secant 1, 2, 3, 4 in here. Left blanks if you want to, include some more. But the idea is that just like on the previous one, we want to start off some distance away from our a value and start slowly working our way closer and closer. I recommend cutting it off here. Don't worry about the rest of this. All right, because again, we're looking for the tangent line slope at 0, which is probably going to be something like this. If I had to put a ruler on it, like in 7th or 8th grade, if they said at 0, what do you suppose the slope of the tangent is? Draw lines. You probably slap your ruler on in some fashion, something like this, and then just kind of measure rise over run. That's a pretty good way to get an estimate of what the tangent line slope would be, but we want exactitude, right? So on this interval, we want some convenient values for sine. Right, so what are some convenient values for sine? I'll label them on the graph. Pi over, we got pi over 2, so in this interval, give me a couple more. We need a total of 4. Pi over 6, okay. Pi over 4.
Do we have to do it in like pi values, or can we do it in numerical?
You'll get cleaner numbers if you do it with pi's.
Do pi over 3.
Pi over 3, yeah. All right, so that's 4 values right there, right? So that's good. Now we want to work from the furthest or farthest, I don't know, English, x value away, start with that one, and then work our way in. All right, so I'll start with the pi over 2 and dial it back. Pi over 3, pi over 4, pi over 6. All right, so that's establishing points on our curve here, 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 and here. So our secants would look something like this. And you can see that the slope of those lines are getting closer and closer to what I think the slope of the tangent would be. All right? So now the hard part. What is the sine of pi over 2? 1. The sine of pi over 3.
Radical 3 over 2.
Radical 3 over 2. Sine of pi over 4.
Radical 3 over 2.
And the sine of pi over 6.
1/2.
1/2. All right, those are some unit circle or hard chart values. All right, pretty easy to come by. Now we know that the h distance, that horizontal distance, is whatever your b value is minus your a value. This is convenient because our a value is 0. So take each b and subtract 0 from it. So basically we're just rewriting b. All right, so we need change in y over change in x. But we discovered earlier, and that was kind of the point, slope of the secant, I'll write it down here again, f of b minus f of a over b minus a. So if I take my f of b and subtract from it my f of a, it's just going to be my f of b again, right? So in this case, and we already know that the b minus a is just the b column, or h if you want, right? So in this case here, really all we're doing, so I'll just make a note. In this case, because it would be f of b minus 0 over b minus 0, it's just whatever your f of b value is divided by your b value. And for that, you want to go to the calculator, because decimals are actually going to work in your favor here. Because you could get an answer like clean-ish answers in fraction form. The problem with those clean-ish answers in fraction form is that they don't tell you much about the size, right? The decimals will. So basically my f of b column divided by my b column. So divided by pi over 2. Radical 3 over 2 divided by pi over 3.
B is 0.
I know it's easy in this situation, but how would you find h? I can't understand if it wasn't easy.
Radical 2 over 2.
Well, wouldn't be that always like necessarily
Divided by pi over 4.
Because like, say for example, so like.
So let me just chuck a few of these values in there. I'll go, I think 2 decimal places ought to do it. So 0.64, 0.83 approximates.
Because here, the
0.90. Let's see what the next one would give us.
yeah, B minus.
They do seem to be increasing. It's just a question of, are they increasing without bound, or are they increasing towards something?
Because it's the final distance. It's the final
Increasing, it seems to be towards 1, right?
original.
So about 0.95 for this one.
You know what I mean? Like so say they're finding that's like 1.1.
Now, if you're convinced at that point that it's going to 1, you're good. But I don't know, maybe it's a trick question. Maybe the slope is going to 0.95. So what I want to do is take another couple of points, because I'm not convinced. So I'm going to do another couple of zeros. I'm going to do pi over 12 and pi over 24. I don't know, you can do whatever you want. Just need something smaller and smaller. The f of b, I don't want to figure that out in decimal form. What I'll do instead of that is I'll just write it as the sine of pi over 12 and the sine of pi over 24. The next column is just a reproduction of b, so that's just pi over 12, pi over 24. So I'll just run another couple of calculations. Yeah, it's going to go to 1, but this wasn't telling us, but these guys will. So divide this. Sine, it's a little cleaner to write it this way. Sine of pi over 12, I think it'd be divided by pi over 12. And then do the same thing with 24. And now you can see it's almost screaming at you that it's approaching 1. So I'll say 0.99 and then 0.997. Approaching.
Cool.
So we know that the slope of the tangent line would be 1. And that would be the derivative.
like limit as h approaches 0 equals 1?
No, the table is actually providing the limit approach. So the only time we actually need to use the limit approach, actually writing a function and finding the limit of it, is when we're doing it algebraically, which I'm going to show you how to do starting tomorrow.
Okay, so this is graphically.
This is graphically.
Do you want to sign?